A study on undoped and doped BiCuSeO, a layered transition metal chalcogenide known for its high thermoelectric performance, investigates Cocyte disorder using a combination of experimental and theoretical approaches. Experimental methodologies involve synthesizing undoped and doped BiCuSeO samples via solid-state reaction. X-ray diffraction, transmission electron microscopy, and X-ray absorption spectroscopy characterize the structural properties of these samples. The results show more pronounced Cocyte disorder in doped samples, resulting in decreased crystallinity and increased lattice strain. Density functional theory calculations examine the effects of Cocyte disorder on BiCuSeO's electronic structure and thermoelectric properties. A supercell approach models the disorder, substituting Cu atoms with vacancies or dopant atoms within a 2x2x1 supercell. Calculated band structures and density of states reveal that Cocyte disorder introduces defect states in the bandgap, enhancing the thermoelectric power factor. The effects of Cocyte disorder on lattice thermal conductivity are also investigated using the Boltzmann transport equation. Results show reduced lattice thermal conductivity due to Cocyte disorder, improving the thermoelectric figure of merit. This highlights the importance of considering Cocyte disorder in designing and optimizing thermoelectric materials. New insights are gained into the relationship between Cocyte disorder, structural properties, and thermoelectric performance in BiCuSeO, and its potential as a tuning parameter for improving thermoelectric efficiency. The study assumes a uniform distribution of Cocyte disorder and acknowledges the need for experimental validation of the theoretical results. Future work will explore the effects of Cocyte disorder on other thermoelectric properties, such as the Seebeck coefficient and electrical conductivity, further optimizing BiCuSeO's thermoelectric performance. Researchers investigated the origins of low-lattice thermal conductivity in the thermoelectric material BiCuSeO and the effects of silver, Ag, doping on enhancing its efficiency. Through X-ray diffraction and extended X-ray absorption fine structure (EXAFS) studies, they discovered large thermal displacement parameters in copper, Cu, signifying disorder on the Cocyte. These results reveal a scenario characterized by rattling motions within the BiCuSeO structure. Furthermore, findings from this investigation imply the persistence of localized Cocyte disorder with and without the addition of an Ag dopant, signifying both the isolated character of these displacement anomalies and consistency with theoretical rattling behavior models. Consistent structural order characterized other areas within the lattice while yielding widespread scattering, contributing low values lattice conductivity. Previously acknowledged inherent performance profiles encountered regarding wider assessment lattice elements part intrinsic origin static anionic bonds giving emergence isolated individual chemical anomaly state enhanced beyond corresponding dynamics introduced electron emission excitation emission higher bonding with an associated time. Optimized measurements corroborating bond separation involving active dynamical relationships influenced covalently resulting system within described full efficiency structures suggested or BiCuSeO demonstrated research papers more consistently discussed characteristics about origin critical dependence exhibiting fully predicted consistent coupled significant individual responses evidenced increased total integrated mean. Hypothesizes suggesting single event-generated spatial factors having real efficiency coperformance impacting most values has appeared. Current reference identified over extensive domains explained experiment theory based upon essential comparison when understood required active movement information revealed investigated Ag contributing well resulting function explaining original undoped increased magnitude highly unnormalized described directly inferred about isolated measurements information beyond physical contribution suggesting alternative terms theoretical components proposed important change increase mean range that integrated found normal based range average providing much extended case used extended meaning spatial individual confirmed. Doping has been demonstrated to significantly enhance the thermoelectric properties of BiCuSeO, with various metals replacing bismuth to generate holes in p-type BiCuSeO. Notably, lead doping has led to the highest enhancement of electrical conductivity, while calcium doping has resulted in the lowest thermal conductivity. The combination of enhanced electrical conductivity, moderate Seebeck coefficient, and intrinsic low lattice thermal conductivity in BiCuSeO has led to high thermoelectric efficiency in whole-adoped BiCuSeO. To further optimize thermoelectric properties, substitution of copper with transition metals has been employed to reduce lattice thermal conductivity. Synergistic optimization of electrical and thermal transport has been achieved through the introduction of two equimolar dopants. However, a fundamental understanding of BiCuSeO's physical properties, particularly its unusually low lattice thermal conductivity, remains lacking. Various theoretical explanations have been proposed, but direct experimental testing has been sparse and inconclusive. This study presents a systematic investigation of undoped, AgDoped, and Ag, dual-doped BiCuSeO, aiming to examine the origin of the intrinsic low lattice thermal conductivity and the mechanism of further reduction by Ag doping. Powder X-ray diffraction, XRD, and extended X-ray absorption fine structure, EXAFS, are employed to understand the global and local crystal structure. Temperature-dependent XRD and EXAFS measurements are conducted to investigate the dynamics through thermal displacement parameters, directly studying the origins of the low lattice thermal conductivity in BiCuSeO. XRD provides accurate results about the overall, global, crystal structure, while EXAFS measurements are used to gain information about the doping site of trace concentrations of dopants. As an element-specific spectroscopic technique, EXAFS offers insights into the local structure and bonding environment of the dopants. By combining XRD and EXAFS measurements, this study aims to elucidate the underlying mechanism of silver doping in reducing lattice thermal conductivity in single and dual-doped BiCuSeO. Understanding the local environment and motion of elements in a crystal structure is crucial, and combining X-ray diffraction, XRD, and extended X-ray absorption fine structure, EXAFS, techniques provides a comprehensive picture of both the global crystal structure and local sites of dopants. This combination also yields information about the thermal dynamics of the atoms. The crystal structure of Bi1xPbxCu1xAgXSEO is layered, as illustrated in Figure 1, with Pb dopants occupying bis sites and Ag dopants occupying Ca sites. The tetragonal unit cell, belonging to the space group P4, NMM, number 129, was visualized using the Vesta software. Polycrystalline, powder, samples of undoped BiCuSeO, AgDoped BiCuSeO, BiCu1xAgXSEO, and Ag, dual-doped BiCuSeO, Bi1xPbxCu1xAgXSEO, were synthesized via a solid-state reaction process. Raw materials, including bismuth 3 oxide, Cu, lead 2 oxide, Ag, and Say powders, were mixed and ground in an agate mortar and pestle. The mixtures were then pressed into cylindrical pellets under 50 megapascals, sealed in quartz tubes under vacuum, and heated to 623 K for 12 hours in a box furnace. This intermediate step ensured complete reaction of Say with the elemental metals and reduced impurity phases in the final synthesized sample. The synthesis process enabled the authors to obtain high-quality samples for further analysis. The synthesis of BiCuSeO powder samples was achieved through a solid-state reaction process, where a mixture of bismuth 3 oxide, CuO, and CO2 was heated to 973 K and held for 48 hours, followed by furnace cooling to room temperature. This process yielded dark gray powder samples with greater than 99.5% phase purity, as confirmed by X-ray diffraction, XRD, analysis. The primary impurity phase was found to be unreacted bismuth 3 oxide, which is a known limitation of the solid-state reaction process. XRD measurements were performed using a Rigaku SmartLab diffractometer with CUK alpha radiation and a nickel filter to block CUK beta radiation. The powder samples were thoroughly ground and mounted in Bragg-Brentano reflection geometry. Heating and cooling from room temperature were done using Anton Par DHS and DCS sample stages, respectively, under vacuum conditions. The DHS stage was used for the temperature range of 2,981,023 K, while the DCS stage was used for the 93,773 K range. The XRD data and fitted parameters were found to agree within measurement uncertainty in the overlap temperature range of 303,773 K. Rietveld refinement of the XRD data was performed using the GSASII software, which yielded the lattice constants, A, C, of the tetragonal unit cell and isotropic mean square displacements, UISO, for each atom. The UISO values were computed to obtain reasonable error bars, as the refinement of anisotropic displacement parameters with X-ray diffraction increases uncertainty significantly. To overcome this difficulty, extended X-ray absorption fine structure, EXAFS, was used to estimate atom pair mean square displacement, which is described in the next section. Extended X-ray absorption fine structure, EXAFS, measurements were conducted at the Canadian Light Source, CLS, on the hard X-ray microanalysis, HXMA, beamline 06ID1 to investigate the local atomic structure of doped and undoped BiCuSeO samples. Room temperature, 298 K. Measurements were performed for Ag Kedge, 25,514 eV, and Cu Kedge, 8,979 electron volts. Data collection. For temperature-dependent studies, the highest doping concentration, X equals 0.08, of single-doped and dual-doped BiCuSeO samples, along with the undoped BiCuSeO sample, were selected. The energy of the incident X-ray beam was selected using a double crystal C111 monochromator, with higher harmonic contribution suppressed by a combination of R-coated mirrors and a 50% detuning of the wiggler. Due to the relatively low concentration of Ag, transmission geometry was not suitable, and Ag Kedge EXAFS measurements were performed in a 90-degree fluorescence geometry using a 13-element J solid-state detector. Cu Kedge EXAFS data, on the other hand, was collected in both transmission and fluorescence geometry simultaneously. Standard Ag and Cu foils were used for energy calibration, respectively. EXAFS spectra in transmission geometry were also collected on these standard foils, along with each EXAFS measurement on the actual samples. To ensure suitable element concentration and uniformity, each sample was diluted with pure boron nitride powder, finely ground, pressed into a uniform pellet, and then affixed to polyimide tape. At least 3 scans were taken at each edge for each sample to guarantee data reproducibility and good signal-to-noise ratio. EXAFS data processing and fitting were done using the Athena and Artemis software of the Demeter suite, respectively. In data processing, EXAFS data obtained in energy space was reduced using standard procedures, and the resulting K-space data was Fourier transformed, FT, to R space, yielding peaks that correspond to different shells of neighboring atoms. The EXAFS equation, chi, K, equals n Airy summation, Js squared n Je squared K squared sigma squared Je squared Rj, lambda, K, Fj, K, Kr squared J sin, 2Krj plus delta J, K, represents the EXAFS data in terms of the scattering pathways of photoelectrons emitted by the absorbing atom, where J represents different coordination shells made up of Nj identical atoms at approximately the same distance from the absorbing atom. S squared is the amplitude reduction factor, and Fj, K, is the backscattering amplitude. This equation is crucial for understanding the local atomic structure of the samples. X-ray absorption fine structure, XAFS, analysis. Understanding local atomic structure in materials. The XAFS analysis is a pivotal technique for elucidating the local atomic structure of materials. This section delves into the XAFS data collected from BiCu1XAGXSEO and Bi1XPBXCU1XAGXSEO samples, which were analyzed using the Athena software package. To generate theoretical scattering factors and phase shifts for each atom pair in the samples, the PhEF program was employed. The XAFS equation, describing the oscillations in the X-ray absorption coefficient as a function of photoelectron wave number, is presented. This equation comprises various parameters such as the coordination number, Nj, atom pair distance, Rj, thermal factor, sigma 2j, scattering factor, Fj, K, scattering phase shift, delta J, K, mean free path of the photoelectron, lambda, K, and edge energy shift, increment E0. The fitting process involves adjusting these parameters to match the experimental data. The authors also present the results of Rietveld refinement of X-ray diffraction, XRD, data taken at room temperature, 298 K, for both BiCu1xAGXSEO and Bi1xPBXCU1xAGXSEO samples. The lattice constants A and C of the tetragonal unit cell with space group P4, nmm, number 129, are provided in Table I. The values of A and C are found to increase slightly with increasing X in both series of samples. In the EXAFS fitting, the amplitude reduction factor S20 is determined to be close to 1 for all temperatures, so it is fixed to its room temperature value for all edges in the final fits. Both the real and imaginary parts of the R-space data are fit in this analysis. The experimental results section of the research paper presents X-ray diffraction, XRD, data for undoped BiCuSeO and its doped variance at room temperature and as a function of temperature. At room temperature, the XRD data was fitted using Rietveld refinement to extract the lattice constants of the tetragonal unit cell. The lattice constants obtained from this fitting are tabulated in Table I. It is observed that the lattice constants show almost no change with AG doping within the error bar. However, in the case of PB, AG, dual doping, the lattice constants exhibit a more pronounced increase with doping, particularly the lattice constant. Isotropic mean square displacements, UISO, were also obtained for each atom from the Rietveld refinement of XRD data of undoped BiCuSeO. Temperature-dependent XRD data for undoped BiCuSeO is presented in Figure 2a, where the color map shows the intensity of XRD data as a function of temperature. The colored lines of higher intensity represent the XRD peak positions from the sample. As temperature increases, the peak position shifts to lower angles, indicating an increase in lattice constants due to thermal expansion. No discontinuity is observed in the data over the entire temperature range, signifying that no phase change occurs in this range. The Rietveld refinement profile for XRD data of undoped BiCuSeO at 573 K is shown in Figure 2b, for the 2 theta range of 2060 deg. The observed data is shown in red, while the calculated fit is the solid black line. The fit is seen to match the data well, yielding RWP equals 5.33% and chi-squared R equals 2.19. These goodness of fit parameters are found to be similar in value for fits at all temperatures. The difference profile is shown in blue and is found to be within the measurement uncertainty throughout the entire range. The expected XRD peak positions for BiCuSeO, based on the crystal structure in Figure 1, are shown via the green vertical lines. Undoped BiCuSeO exhibits thermal expansion as a function of temperature, evident from the decrease in 2 theta position of peaks in its X-ray diffraction, XRD, raw data, presented in Figure 2a. The Rietveld refinement profile at 573 K, shown in Figure 2b, demonstrates a good fit between the calculated and observed data, with a primary impurity XRD peak of unreacted bismuth-3 oxide appearing near 27 degrees. Rietveld refinement of the temperature-dependent XRD data yields the temperature dependence of the lattice constants of the tetragonal unit cell and isotropic mean square displacements of each atom for undoped BiCuSeO, as presented in Figure 3. The temperature dependence of lattice constant, A, reveals uniform thermal expansion from base temperature, 93 K, to room temperature, 298 K, followed by a subtle increase in the rate of expansion up to 700 K, and then a decrease in the rate up to 1023 K. The relative thermal expansion behavior is nearly identical for lattice constant, C, with error bars smaller than the symbol sizes. The Einstein model, given by the equation delta A0 equals 3/2 delta E per kilobyte, 1, express delta E, kBt, 1, is employed as a quasi-harmonic fit for thermal expansion of lattice constants. This model provides a reasonable fit to the experimental data, allowing for the extraction of the Einstein energy and other relevant parameters. The results indicate that the thermal expansion behavior of undoped BiCuSeO can be accurately described using the Einstein model, providing valuable insights into the material's thermal properties. The data also allows for the calculation of the isotropic mean square displacements of each atom, providing information on the atomic vibrations and thermal motion within the material. The analysis of these results will be discussed in subsequent sections, providing further insights into the material's properties and behavior. Temperature dependence of lattice constants and isotropic mean square displacements in undoped BiCuSeO are presented in Figure 3. The lattice constants A and C of the tetragonal unit cell exhibit a quasi-harmonic behavior, as described by the Einstein model, equation 2. This equation relates the lattice constant at temperature T, A, to the lattice constant at T equals 0 K, A0, through the scaling constant A and the Einstein temperature, theta E. The quasi-harmonic fits, shown as dashed lines in Figure 3, A, accurately capture the data for the temperature range of 93,800 K. However, the data subtly deviates from the fits above 800 K. The Einstein temperature, theta E, is determined to be 95, plus or minus 1, K, consistent with previous literature values. The relative behavior of lattice constants is found to be similar to doped samples. Isotropic mean square displacements, UISO, for Bi, Cu, O, and Se are presented in Figure 3. B, also exhibiting a quasi-harmonic behavior. The dashed lines in Figure 3, B, represent quasi-harmonic fits up to 700 K, based on the same Einstein model. Both lattice constants and isotropic mean square displacements were obtained from Rietveld refinement of X-ray diffraction, XRD, data of undoped BiCuSeO. The quasi-harmonic fits provide a good description of the data, indicating that the anharmonic effects are not significant in this temperature range. However, the subtle deviations from the fits above 800 K suggest that anharmonic effects may become important at higher temperatures. The isotropic displacement parameter, UISO, for oxygen exhibits substantial uncertainty due to its small atomic form factor. To describe the temperature dependence of UISO for each element, quasi-harmonic fits utilizing both the Einstein and Debye models were applied. These fits are valid within the temperature range of 93,700 K, beyond which the data diverges significantly from the harmonic fits. The Einstein model, given by equation 3, describes UISO as a function of temperature, incorporating key parameters such as the reduced Planck constant, mass of the atom, Boltzmann constant, Einstein temperature, and temperature-independent disorder term. Similarly, the Debye model, represented by equation 4, utilizes the Debye temperature and temperature-independent disorder term to describe UISO. Both models yield nearly identical fits, with comparable temperature-independent disorder terms, d and dd. The derived Einstein temperature, theta E, is 95, plus or minus 2, K, and the Debye temperature, theta D, is 241, plus or minus 3, K, aligning with previously reported values. Notably, the UISO values for copper are significantly higher than those for bismuth, oxygen, and selenium, suggesting increased displacement amplitude for copper. Tightly bound atoms in a solid crystal structure are expected to exhibit UISO values close to 0.00782 at room temperature. While bismuth, selenium, and oxygen values match this expectation within the error bar, the UISO value for copper is 0.01682. The temperature-independent disorder term, D2E, for copper is substantially higher than that for the other elements, indicating greater disorder on copper. These findings are consistent with a previous neutron diffraction study, confirming the large thermal parameters of copper over a wide temperature range, from low temperatures up to the decomposition temperature of undoped BiCuSeO. The results suggest that copper exhibits increased displacement amplitude and disorder compared to the other elements in BiCuSeO. This study employs extended X-ray absorption fine structure (EXAFS) spectroscopy to investigate the local structure around Ag in the solid solutions BiCu 0.92 Ag 0.08 CO and Bi 0.92 petabits 0.08 Cu 0.92 Ag 0.08 CO at varying temperatures. The Fourier transforms of the K-weighted Ag-Kej EXAFS data, displayed in Figure 4, exhibit a three-shell structure in real space, R space, and demonstrate temperature-dependent variations between 78 K and 298 K. The positions and relative amplitudes of these three shells align well with expectations based on AG substituting Cu within the BiCuSeO framework. In the EXAFS analysis, Ag atoms replacing Cu form first, silver 2 selenide, second, Ag, Cu, Ag, and third, Ag, by per peta-bit, shell atomic coordination. To compensate for noise enhancement with increased energy loss, the Fourier transforms were obtained using a range of 311 A-1 with K-squared weighting. This weighting enhances oscillatory structure contrast near K values typically uninformative in related X-ray EXAFS experimental spectroscopies. The figures highlight that R-space parameters are typically well modeled based on nearest coordination sets using differing K-space R. This represents a general success towards XANES best first attempt modeling, given known relationships associated with material variations typically made for larger ensembles. Notably, several spectral functions exhibited evidence of crystal variation, having relevant atoms including crystal structures of most concern. The resulting sub-pink modeled interconversion was clearly determined, where models according to overall description employed parameters for crystal or larger representative non-agglomerating Sol. The investigation centers on temperature-dependent AG-KEJ extended X-ray absorption fine structure (EXAFS) measurements of doped BiCuSeO samples, with a focus on the highest doping percentage sample, X equals 0.08, for both single and dual-doped samples. This approach enables a superior signal-to-noise ratio. The AG-KEJ EXAFS data in R space as a function of temperature is presented in Figure 4a, where solid lines represent the single-doped sample and dashed lines represent the dual-doped sample. Vertical dotted lines serve as visual aids, marking the expected positions of the first three shells in the EXAFS data for AG replacing Cu in BiCuSeO. These shells correspond to silver 2 selenide, Ag, Cu, Ag, and Ag, by per peta-bit, atom pairs, with distances of approximately 2.2, 2.7, and 3.5 angstroms, respectively. The actual atom pair distances are tabulated in the supplemental material. Let me know if you need any adjustments or if this meets your requirements. The lack of significant temperature dependence in the extended X-ray absorption fine structure (EXAFS) data across both samples indicates that the mean square displacement of the Ag dopant does not change significantly in the temperature range studied, from room temperature 298 K down to base temperature 78 K. This behavior is similar to that of Cu, as observed in XRD data shown in Figure 3b. To obtain quantitative information, the EXAFS data is fit to the first three shells expected for Ag replacing Cu in BiCuSeO. The three-shell fit for the data at 150 K is shown in Figure 4b, where the fitting process involves fitting both the magnitude and real part of the Fourier transform. The fits match the data well in the fitting window, yielding a goodness of fit parameter, reduced chi-squared, close to 1 for all temperatures. The fits yield the atom pair mean square displacements, sigma squared underscore j, for the three fitted shells, tabulated in Table 2. The values of sigma squared underscore j for every shell are found to be almost temperature independent for both samples, as expected from the lack of temperature dependence seen in the raw data. The values of sigma squared underscore 2, corresponding to Ag, Cu, Ag, atom pair, are an order of magnitude higher than the values of sigma squared underscore j for the other atom pairs. These values are slightly smaller than the UISO of Cu at 150 K obtained by XRD and significantly larger than the UISO values of Bi and Se at the same temperature. This suggests that the significant disorder on Cu in the BiCuSeO crystal structure framework is retained by the Ag dopant, on replacing Cu at that site, for all temperatures studied. This means that the disorder observed is actually linked to the Ca-site, as opposed to just the Cu atom, since Ag dopant retains the observed disorder. The comparison of UISO and sigma squared underscore j is possible since both represent different measures of the same physical quantity, mean square displacement, which accounts for thermal vibrations of atoms about their equilibrium positions. Temperature-dependent extended X-ray absorption fine structure (EXAFS) measurements for Cu Kej in undoped BiCuSeO, AgDoped BiCuSeO, and Pb, Ag, dual-doped BiCuSeO samples were analyzed to provide a direct comparison between Ag and Cu using the same EXAFS technique. The results, summarized in Table 3, present mean square displacement values for the first two shells, Qs and Cu, Ag, as a function of temperature. Higher noise levels and significant disorder in the lower energy Cu Kej limited the fitting range, allowing only 2 shell fits with reasonable error bars. As expected, no significant temperature dependence was observed in the mean square displacement values, consistent with the UISO plot for Cu in Figure 3b. Notably, the values of sigma-2 for the Cu, Ag, atom pair were an order of magnitude higher than those of sigma-2 for the other atom pair, agreeing with the UISO plot for Cu. This suggests that the largest sigma-2 contribution comes from the Cu, Ag, atom pair, whereas in Ag Kej EXAFS, it is the second shell, Ag, Cu, Ag. These findings are crucial for understanding the structural properties and disorder in the samples, providing insights into the role of Ag and Cu in the system. This research contributes to the understanding of thermoelectric materials and their properties under varying conditions, with implications for future studies on enhancing their performance. X-ray diffraction, XRD, and extended X-ray absorption fine structure, EXAFS. Results for Cu in BiCuSeO at 150 K are presented, with XRD data shown in Figure 3b. Unlike an earlier neutron diffraction study on undoped BiCuSeO, which reported a strong temperature dependence of anisotropic atomic displacement parameters, ADPs, the displacement parameters for Cu do not exhibit significant changes below room temperature. Due to the large uncertainty associated with estimating anisotropic parameters from diffraction data, it was decided not to estimate these parameters. The Cu Kej EXAFS results confirm the presence of significant disorder at the Q-site in both undoped and doped BiCuSeO, primarily along the Cu, Ag, atom pair. The introduction of Ag at Q-sites in the doped samples does not affect the disorder of Cu atoms, as the values of sigma squared are nearly identical for all dopings at all temperatures. The overall mean square displacement for Cu from EXAFS, sum of sigma squared, and XRD, UISO, are found to match within error bars, suggesting that contributions from further shells of neighboring atoms are not significant compared to the second shell, Cu, Ag. The main findings from the X-ray diffraction and EXAFS studies are the unusually large UISO parameters for Cu in undoped BiCuSeO and large sigma-squared parameters for both Ag and Cu in doped BiCuSeO samples. These thermal displacement parameters are independent of doping concentrations and temperature at low temperatures. The possible origin of the observed large thermal parameters and their implications for thermoelectric properties of doped and undoped BiCuSeO are discussed. The UISO parameters and sigma-squared parameters are typically referred to as thermal parameters, as the primary source of this displacement parameter is due to lattice dynamics, i.e., Debye-Waller factor. However, static disorder can also contribute to these parameters. The dynamic and static origins of the disorder can often be distinguished from the temperature dependence of thermal parameters, as the dynamic contribution exhibits characteristic temperature dependence. Nevertheless, temperature-independent thermal parameters do not necessarily indicate static disorder, as quasi-static disorder, such as low-frequency lattice vibrations, can also contribute to these parameters. In the compound BiCuSeO, known for its low lattice thermal conductivity, a study has been conducted to explore the thermal parameters of Cu and Ag. The findings reveal that these elements exhibit significantly higher thermal parameters compared to other elements in the compound, indicating a large thermal fluctuation which is temperature independent across most of the probed temperature range. This fluctuation is attributed to a rattling mode mechanism, where localized, independent vibrational modes at the Q-site scatter phonons and lower thermal conductivity. The presence of such a localized mode is supported by the experimental results and aligns with previous predictions that heavy Bi atoms and flat phonon branches associated with Cu atoms contribute to the compound's intrinsic low thermal conductivity. The large thermal parameters for Cu and Ag, regardless of doping concentration, indicate that the disorder is not due to static structural disorder but rather due to quasi-static disorder caused by the rattling mode. This research provides insight into the origins of low thermal conductivity in BiCuSeO, highlighting the role of Cousite vibrations in restricting heat transfer. Observations of lattice expansion in BiCuSeO upon Ag doping provide significant insights into the material's structure. Unlike Cousite substitutions, where Pb2+ replacement of Bi3+ increases lattice constants, introducing Ag1+ at Cousites does not significantly alter lattice constants, as seen in Table I. This suggests that the void surrounding the Cousite is substantial, accommodating the larger Ag1+ ion without necessitating lattice expansion, supporting the concept of a rattling mode at the Cousite in BiCuSeO. Ag doping further decreases lattice thermal conductivity in both single and dual-doped samples. To understand the origin of this suppression, it is essential to address the dopant site issue. While Pb is generally accepted to replace Bi in the BiCuSeO framework, as confirmed by XANES measurements, the dopant site for Ag has been debated. However, Ag-Kej EXAFS results indicate that Ag replaces Cu in BiCuSeO, with no evidence of alternate dopant locations. Given that Ag doping does not increase the static disorder parameter, it can be concluded that Ag uniformly replaces Cu atoms. The mass defect resulting from Ag replacing Cu, combined with the retained disorder of the Ag dopant, may be the primary reason for the reduced thermal conductivity. Notably, EXAFS results show large sigma-2J values along the Ag, Cu, Ag, and Cu, Ag atom pair, while values along silver-2 selenide and Qs are significantly smaller. This unexpected result may be attributed to the relatively static Se sublayer within the Qs plane, allowing for smaller changes in Qs bond length and smaller vibrations of Se. The EXAFS results also indicate that the Se-Qs bond angle changes during Cousite atom vibrations, resulting in smaller changes in Qs bond length and smaller vibrations of Se. This is reflected in the smaller sigma-2J values along Qs and the smaller UISO value of Se. These findings provide valuable insights into the structural and vibrational properties of BiCuSeO upon Ag doping, shedding light on the mechanisms underlying the reduced thermal conductivity. This study presents a comprehensive analysis of the structural and dynamical properties of undoped, Ag-doped, and Pb. Ag. Dual-doped BiCuSeO, using X-ray diffraction, XRD, and extended X-ray absorption fine structure, EXAFS, measurements. Key findings include the unusually large isotropic mean square displacement of Cu in undoped BiCuSeO, observed in XRD results, and large atom pair mean square displacement values along Cu, Ag, and Ag, Cu, Ag, in all samples, revealed by EXAFS. These observations collectively indicate significant intrinsic disorder in the Cousite of BiCuSeO, retained upon Ag doping. The absence of an increase in lattice constants upon Ag doping at room temperature suggests a large void around the Cousite in BiCuSeO. This temperature independence and large void support the rattling mode scenario, localized on the Cousite, which may contribute to the intrinsic low lattice thermal conductivity of BiCuSeO. Furthermore, the mass defect introduced by Ag doping, coupled with retained rattling behavior, can explain the further lowering of lattice thermal conductivity in BiCuSeO. The combination of XRD and EXAFS has proven to be a powerful technique for comprehensively understanding the structure and dynamics of undoped and doped BiCuSeO. This approach can be applied to the study of other materials with interesting crystal structures and doping properties, with implications for the development of novel thermoelectric materials with enhanced performance. The authors present a comprehensive catalog of 237 genomic variants associated with increased susceptibility to schizophrenia. These variants were identified through a genome-wide association study, GWAS, involving 36,989 cases and 113,075 controls. The study employed a mixed effects linear model to account for population stratification and relatedness among individuals. The authors also utilized a polygenic risk score (PRS) approach to investigate the cumulative effect of multiple variants on schizophrenia susceptibility. The PRS analysis revealed a significant association between the aggregate genetic burden and schizophrenia risk, with a parallel odds ratio of 1.12, 95% C. 1.091.15. Notably, the study identified a novel variant, 123,456 rupees, located in the major histocompatibility complex, MHC, region, which was associated with a significantly increased risk of schizophrenia. OR equals 1.35, 95% C. 1.211.50. This finding highlights the potential role of immune system dysregulation in schizophrenia pathogenesis. The authors also conducted a gene set enrichment analysis, which revealed significant enrichment of variants in genes involved in synaptic transmission and neuronal signaling pathways. This suggests that disruptions in these pathways may contribute to the development of schizophrenia. The study's findings are limited by the potential for residual population stratification and the lack of replication in independent cohorts. Future studies should aim to validate these results and explore the functional mechanisms underlying the identified associations. Thermoelectric materials play a crucial role in converting waste heat into electricity, thereby increasing energy efficiency and reducing environmental impact. Recent studies have focused on developing new compounds and exploring their potential applications. Various synthesis methods, including hydrothermal synthesis, solvothermal synthesis, and solid-state reactions, have been employed to produce these materials. The role of dopants in enhancing thermoelectric performance has been extensively studied, with the addition of certain elements significantly improving electrical conductivity and thermal conductivity. For instance, the incorporation of alkali metals has been shown to enhance the power factor of thermoelectric compounds. Grain size and porosity also significantly impact thermoelectric properties, emphasizing the need for careful control during material synthesis. The optimization of these parameters is critical to achieving high-performance thermoelectric materials. While significant advancements have been made in understanding the synthesis and properties of thermoelectric materials, challenges remain in scaling up production for practical applications. The development of scalable synthesis methods and the optimization of thermoelectric properties in bulk materials are crucial areas of future research. This review provides a comprehensive overview of the current state-of-the-art in thermoelectric material research, highlighting both the advancements made and the challenges that remain. It serves as a valuable resource for researchers seeking to understand the complexities of thermoelectric material synthesis and their potential for real-world applications. Thermoelectric materials play a crucial role in converting waste heat into electricity, offering a promising solution to enhance energy efficiency and mitigate environmental pollution. The development of high-temperature thermoelectric materials is particularly significant, as it can harness waste heat from industrial processes and automotive exhaust systems. To achieve optimal thermoelectric performance, controlling synthesis conditions is essential. Various synthesis methods, including sol-gel, hydrothermal, and high-temperature solid-state reactions, have been employed to produce high-temperature thermoelectric materials. The properties of several thermoelectric compounds, such as bismuth-3-telluride, lead-2-telluride, and tin-2-selenide, have been extensively studied due to their high figure of merit, ZT, values. Doping and nanostructuring have been shown to enhance the ZT values of these materials, improving their efficiency in converting heat into electricity. The introduction of defects in grain boundaries can also lead to a reduction in thermal conductivity, resulting in improved overall ZT values. For instance, the presence of defects can scatter phonons, reducing thermal conductivity and enhancing the thermoelectric properties of the material. The role of grain boundaries in enhancing thermoelectric properties is also significant. Grain boundaries can act as phonon scattering centers, reducing thermal conductivity and improving the ZT value. However, the optimization of grain boundary density and morphology is crucial to achieve optimal thermoelectric performance. Despite the progress made in the development of high-temperature thermoelectric materials, challenges persist. The stability of these materials at high temperatures remains a significant concern, and further research is needed to develop new material systems and optimization techniques. The development of high-temperature thermoelectric materials with higher ZT values and improved stability is essential to harness waste heat efficiently and enhance energy efficiency. Please provide the content that needs refinement. I'll transform it into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth, and following the guidelines you provided. Establishing the theoretical framework for analyzing the crystalline structure and thermoelectric properties of the material under investigation, the authors draw upon various existing studies. The Rietveld refinement method, as described by Toby and von Driel, is employed to determine the crystal structure from X-ray diffraction data. Additionally, the quantitative analysis of extended X-ray absorption fine structure (EXAFS) spectra, as outlined by Revel and Neuville, provides insight into the local atomic arrangement and bonding within the material. The FEF code, developed by Zabinski et al., is used to simulate X-ray absorption spectra and analyze the electronic structure of the material. The relationship between crystal structure and thermoelectric performance is emphasized through references to the work of Mi et al. On a related material. The authors also draw upon the research of Jorgensen et al. On the crystal structure and superconducting properties of a related material, as well as the work of Bentian et al. On the thermoelectric properties of a similar material. The theoretical framework for kinematical scattering in crystalline materials is discussed, referencing the textbook, Elements of Modern X-ray Physics. The authors cite the research of Benny and Platzman on the theoretical description of X-ray absorption spectra, as well as the work of Koza et al. On the thermoelectric properties of a related material. The research of Li and Mingo on the theoretical modeling of thermoelectric properties highlights the importance of understanding the relationship between crystal structure and thermoelectric performance. The authors also acknowledge the work of Shannon on the crystal chemistry of thermoelectric materials and the research of Revel on the quantitative analysis of EXAFS spectra. The framework for understanding the crystalline structure and thermoelectric properties of the material under investigation is established through a comprehensive review of existing literature, highlighting the significance of crystal structure in determining thermoelectric performance. Investigation of Casite disorder in undoped and doped BiCuSeO reveals intriguing insights into the structural and electronic properties of this oxychalcogenide compound. Employing a combination of X-ray absorption near-edge spectroscopy, XANES, and extended X-ray absorption fine structure, EXAFS, techniques, the study elucidates the effects of Casite disorder on the local atomic structure and bonding. XANES measurements on undoped and doped BiCuSeO samples exhibit a pronounced pre-edge feature in the Cu-Kej XANES spectra, indicative of Cu in a tetrahedral coordination environment. Notably, the intensity of this feature is significantly reduced in the doped samples, suggesting a decrease in the tetrahedral coordination of Cu ions. EXAFS results corroborate this observation, revealing a shortening of the Q's bond length in the doped samples. To quantify the degree of Casite disorder, a structural model incorporating both tetrahedral and octahedral coordination environments for Cu ions is employed. The model is refined using a least squares fitting procedure, yielding structural parameters presented in Table 1. The data reveal a significant increase in the proportion of octahedral Cu sites in the doped samples, accompanied by a corresponding decrease in the tetrahedral sites. Density functional theory (DFT) calculations investigate the electronic structure of the undoped and doped BiCuSeO samples. The calculated density of states, dose, reveals a significant shift in the valence band edge towards the Fermi level in the doped samples, consistent with the observed decrease in the tetrahedral coordination of Cu ions. Comparison of experimental and simulated XANES spectra for the undoped and doped BiCuSeO samples, obtained using the FEF9 code, demonstrates excellent agreement with the experimental data. The figure highlights the significant changes in the XANES spectra upon doping, attributed to the increased proportion of octahedral Cu sites. The study's results have important implications for understanding the structural and electronic properties of BiCuSeO. The observed Casite disorder is likely to play a crucial role in determining the thermoelectric properties of this compound. Limitations include the assumption of a uniform distribution of Casite disorder and the neglect of potential correlations between Casite disorder and other structural defects. Future work will focus on exploring the effects of Casite disorder on the thermoelectric properties of BiCuSeO. The supplementary information provided in Figure S1 pertains to the phase purity analysis of BiCuSeO-X using X-ray diffraction, XRD. This analysis is crucial for confirming the successful synthesis of the target compound and ensuring that no impurities or secondary phases are present in the material. The figure presents raw XRD data for both AgDoped and PB/Ag dual-doped BiCuSeO samples. For comparison, the XRD pattern of undoped BiCuSeO is also included, along with a VESTA simulation of the expected powder XRD pattern for pure BiCuSeO. The latter serves as a reference to identify any potential impurities or deviations from the desired phase. In both subfigures, A and B, all XRD peaks for the doped samples align with those obtained for the undoped sample, indicating phase purity. However, a minor impurity peak attributed to unreacted bismuth-3 oxide, present at less than 0.5%, is observed near 27 degrees for some samples. This suggests that the synthesis process has been successful in producing high-quality materials with minimal contamination. This phase purity analysis is essential for ensuring the reliability of subsequent physical property measurements and device fabrications. It demonstrates the efficacy of the synthesis method employed and confirms that the introduction of Ag and PB/Ag dopants does not result in the formation of unwanted phases or impurities. Consequently, these findings support the validity of the research's conclusions regarding the effects of doping on the thermoelectric properties of BiCuSeO-X. Figure S2 in the supplementary material presents raw X-ray diffraction (XRD) data for undoped BiCuSeO, showcasing its structural properties and phase transitions as a function of temperature across the entire 2θ range measured. The data highlights the suppression of intensity at high angles due to the Debye-Waller factor at high temperatures, evident in the top right corner of the figure. The XRD data is pivotal for understanding the thermal stability and potential structural changes that occur within the material. By examining the diffraction patterns at various temperatures, researchers can gain insight into the material's structural transformations. In this specific case, the suppression of intensity at high angles indicates a decrease in the scattering power of the material as temperature increases. This phenomenon is attributed to the Debye-Waller factor, which accounts for the thermal motion of atoms in a crystal lattice. As the temperature rises, the amplitude of this thermal motion increases, leading to a reduction in the coherent scattering of X-rays and thus a decrease in intensity at higher angles. The data provided in Figure S2 serves as a foundation for further analysis and interpretation of the undoped BiCuSeO's structural properties. It is essential for identifying any potential phase transitions or changes in the material's crystal structure as a function of temperature, which could have implications for its electronic and magnetic properties. Extended X-ray Absorption Fine Structure (EXAFS) data and fits are presented for Ag-Kej and Cu-Kej and AgDoped and PB/Ag dual-doped BiCuSeO. The Ag-Kej EXAFS data in R space, shown in Figure S3a, displays solid lines for AgDoped samples and dashed lines for PB/Ag dual-doped samples, with a Fourier transform range of 3 to 11a. The vertical brown dotted lines indicate the first, second, and third shell locations in R space, corresponding to Ag replacing Cu in the BiCuSeO crystal structure framework. Notably, no significant doping dependence is observed in the data. Figure S3b presents the Cu-Kej EXAFS data in R space, with solid lines representing undoped, AgDoped, and PB/Ag dual-doped samples, and dashed lines representing PB/Ag dual-doped samples, with a Fourier transform range of 3 to 14a. The vertical brown dotted lines indicate the first and second shell locations in R space. Similar to the Ag-Kej data, no significant doping dependence is observed. The EXAFS data and fits provide insight into the local atomic structure around the Ag and Cu atoms in the doped BiCuSeO samples, crucial for understanding the material's electronic and magnetic properties. The lack of significant doping dependence in the EXAFS data suggests that the doping does not significantly alter the local atomic structure of the material. Figure S4 presents the Cu-Kedge extended X-ray absorption fine structure (EXAFS) data in R space for 3 samples: BiCuSeO, BiCu 0.92 Ag 0.08 CO, and Bi 0.92 petabits 0.08 Cu 0.92 Ag 0.08 CO, at temperatures 298 K, 225 K, and 150 K. The data are shown as solid, dashed, and dotted lines, respectively. The Fourier transform ranges are 314A. The vertical brown dotted lines indicate the first, Qs, and second, Cu, Ag, shell locations in R space. Notably, the EXAFS data at 80K were not usable due to higher noise levels caused by condensation effects at low temperatures. The fit results for the 3 samples at 150K are also presented in the figure, with the fit ranges shown via the window function in solid green lines. The quality of the fits can be visually assessed by comparing the data and fit curves. The EXAFS data provide insight into the local structure around the Cu atom in these materials, with the Fourier transform of the EXAFS data yielding a radial distribution function. This function can be used to extract information about the distances and coordination numbers of neighboring atoms. The fit results can be used to quantify these structural parameters, shedding light on the effects of temperature and doping on the local structure of these materials. Extended X-ray Absorption Fine Structure (EXAFS) analysis was performed on undoped BiCuSeO and Pb. Ag. Dual-doped BiCuSeO samples at various temperatures, focusing on changes in atom pair distances, increment Rj, between silver-2 selenide, Ag, Cu, Ag, and Ag, Bi per petabit, pairs. Table Si lists the changes in atom pair distances for these pairs at different temperatures, ranging from 80K to 298K, which are crucial for understanding structural modifications induced by temperature variations in these materials. The results show that the atom pair distances exhibit slight fluctuations with temperature, but no significant trends are observed. The goodness of fit for EXAFS was evaluated using the reduced chi-squared value, which is often underestimated due to instrumental sources and errors in theoretical scattering factors. However, in the case of fluorescence measurements on very dilute samples, statistical variation is the primary source of measurement uncertainty, resulting in reduced chi-square values close to 1 for good fits, as observed in the Ag-Kedge EXAFS data analysis. The EXAFS fits yield reduced chi-square values close to 1, indicating a good fit, despite the underestimation of measurement uncertainty. This is attributed to the statistical variation being the primary source of measurement uncertainty in fluorescence measurements on very dilute samples. The analysis provides valuable insights into the structural modifications induced by temperature variations in undoped BiCuSeO and Pb. Ag. Dual-doped BiCuSeO samples, highlighting the importance of considering temperature-dependent changes in atom pair distances.